We are going to discuss extreme values of a function. Extreme values are the highest or the lowest values of a function. And we're going to be looking at the closed intervals as well as the open intervals. Extreme value is also called the maximum or the minimum value. So why do we need to find the extreme value? Because this is very useful in everyday life. We have to think what's the most effective size of dose of a medicine, or what's the least possible way to build a building or play yard or whatever. What's the number of items that will give me the maximized profit? So optimization, whenever we want to optimize a function, we need to think about either minimum value or the maximum value when we're thinking about optimization. If you're trying to minimize the cost, then we would be minimizing the function. If you're trying to maximize the profit, we will be maximizing the function. So remember, the location of maximum and minimum is where the derivative is 0 or derivative does not exist. Either derivative is 0 or derivative does not exist. So if you have a function, for example, something like this. So I just did draw a function f of x, and x and y axes are given. So what are the points where I do have maximums and minimums? First of all, there's two kinds of maximums and minimums. One is called global or absolute max and min. Global or absolute max or min. Global or absolute max and min is the highest possible point or the lowest possible point on entire domain of your graph. So highest possible point or the lowest possible point is called absolute or global max or min. Another kind is called local or relative. Local max and min or relative max and min. Local max and min and relative max and min. Local or relative max and min. Local or relative max and min. Local min is a point that's lower than its neighbors. For example, this point is lower than its neighbors, or this point lower than the neighbors. So this point lower than the neighbors. So any point that's lower than its neighbors would be called a local or relative max or min. Absolute or global max min is the absolutely lowest or absolutely highest point of a graph. So absolute, again, we just said that absolute max is the highest possible point. What if you're thinking about on a closed interval? Theorem of existence of extrema on a closed interval. Extreme value theorem. Extreme value theorem, if you have a continuous function on a closed bounded interval, the a, b have brackets around. So these are the points defined for your function. So you have a, let's just say a is here and b is here. This is a continuous function on a closed, this is a continuous function, it's closed and bounded. So this extreme value theorem guarantees that it is going to have an absolute max and an absolute min in that interval. So absolute min will be here and absolute min will be actually here, and absolute max will be here. So this is min and this is max. You will have absolute max and min if you are looking at a closed interval of a function. Closed interval of a function and it's bounded. That means the lower and the upper points are also included in the interval. So local max and min cannot be your endpoints, but absolute max and min can be the endpoints. Local max and min cannot be your endpoints. Local max and min is somewhere in the interval. Like in this case, the local min and absolute min are same for the graph we just did draw. Local max and min cannot be the endpoints because we don't know what's happening. So I cannot say this point is local max because I don't know what's happening to the other side of the graph. Is it going lower? Is it going higher? So we don't really know. So absolute max min can be the endpoints. Local max min will be inside your interval. They cannot be the endpoints. Whenever there's a smile or a frown on the graph, there's a local max or min. So here's an example. This would be local min. This would be a local max, local min and local max. Okay, when you see the word extrema, we're talking about absolute max or min. Or if you see local, relative, max, min, we can also find them just like we find the absolute max and min. So we'll see some examples. Increasing and decreasing function. Let f be a continuous function on the closed interval ab and differentiable on the open interval ab. Why do we say differentiable on the open? Because derivative does not exist at sharp corners. So derivative does not exist at point A and B because they're sharp corners, and we don't know how to draw the slope of tangent line at those sharp corners. So if dash for all x in AB, then f is increasing. So how can we say the function is increasing based on the derivative? We can say if the derivative is positive, then the function is increasing. If derivative is negative, less than 0, the function is decreasing. If derivative is 0, the function is constant. Let's take a look at a few examples. Circle and label appropriately the location and type of relative max and min. So we're looking at relative, which means local max and min in this case. For the first graph, this would be max, this would be min, and there's my max and there's my min. Actually, for the local, remember, it cannot be at the end point, so local cannot be at the end point. So this cannot be, again, if you're looking for local, they cannot be at the end points, but absolute max and min can be at the end points. Okay, absolute max and min can be at the endpoints. Local max and min cannot be at the endpoints. Let's look at some example here. So here we're given a graph of a function. So we do have local max here because this point is higher than the neighbors. We do have a local min here. This point is lower than the neighbors. We have an absolute max here. This is the highest possible point on the graph. And we do have, if the graph is going further, we can say this is a local minimum because it's lower than the neighbors. And this would be the absolute max point for me. Absolute max point for me. All right, absolute max. The lowest possible point on the graph is absolute min. The highest possible point on the graph is absolute max. And the point lower than its neighbors is local min. Point higher than its neighbors is local max. Okay. Now, not every function has maxes and mins. Let's check out f of x is equal to x squared. Does it have a local max? Yes. Where is the local max? It's at x equals 0. Does it have an absolute max? Sorry. Go back. Does it have a local min? Yes, at x equals 0. Does it have an absolute min? Yes, at the same point. Does it have any local max? No, because it's going on forever, and no absolute max either. But if we were looking on a closed interval, the theorem guarantees, if I'm looking at y is equal to x squared on a closed interval, let's say between -3 to 3, then we do have the point that is absolute max and a point that's absolute min. Or let's say -3 to 5, then we do have any interval, any closed interval, we do have the absolute max and absolute min in that case. Okay, f of x is equal to x to the third power. How does that graph look like? That graph looks something like this. Does this point have an absolute max? No. Absolute min? No. Local max? No. Local min? No. How about f of x is equal to 1 over x? Again, let's check out this one, and we're looking at entire domain. No absolute max, no local max, no absolute min, no local min in this case. Remember, if the function is continuous, has a hole defined on the open interval, or has a vertical asymptote, then there's no absolute max or min. So if we have a hole in a function or a vertical tangent, then there would be vertical asymptote, then there would be no absolute max or min for that. So what is a critical point? Now, critical point is a number c in the domain of function. Easy words, critical points are the points which is going to be your max or min. Critical points are the points where your derivative is 0 or it does not exist. So derivative is 0 or it does not exist. In this case, my critical points will be all these points where either the derivative is 0 or derivative does not exist. Fermat's theorem. Fermat says that if c is a local max or min, then c must be a critical point. Remember, we did not say absolute extrema. That's why c cannot be one of the endpoints. So absolute max and min can be endpoints. Relative max or min cannot be endpoints. All extrema occur at critical points, but not all critical points are extrema. Very important to understand that if you have a max or min, then it can only occur at a critical point. But not all critical points are going to give you a max or min. Let's think about f of x is equal to x to the third. What is the derivative of f of x at x equals 0? 3x squared, the derivative is 0. But that is not your max or min. You don't have a max or min at this point. Although you do have a horizontal tangent, but that's neither your maximum nor your minimum. So even though x equals 0 is going to be your critical point, x equals 0 is your critical point, but it's not your max or min. Okay, so not If you have a max or min, it can only occur at a critical point, but not all critical points are going to be maxes or mins. We earlier discussed extreme value on a closed interval. If you are looking at a function, continuous function, smooth continuous function in a closed interval, then it must have an absolute max and absolute min in that interval. For example, here, so I'm looking at, let's just say I'm looking at this function on the interval -7 to 5. Does it have any absolute min? Yes, right over here. Does it have any absolute max? Yes, right over there. Does it have any local min? No, because we don't really know what's happening to this side of the graph. No local max because we don't know what's happening to the other side of the graph. Okay, strategy for finding extrema. Now we're going to look for some functions and try to find the maximum and minimums of those functions, because our goal is to be able to optimize a function or minimize or maximize a function. So first step would be find all the critical points in the closed interval and compute function values at these points. Critical points are the points where either derivative is 0 or it does not exist. Compute function value at the endpoints as well. Use these values to identify the max and min. These can be also used to find, so this table that we're going to make, we can use it to find absolute max min if we have a closed interval. We can also use it to find local max min in that closed interval. If you're looking for extrema, no interval is given. You have to look at the neighborhood of critical points to decide if you have a max or min. So if you're looking for absolute max min and interval is not given, then you're looking at entire domain. So once we have the critical point, we will try to plug in the x values around that point to see if that critical point is a max or min. Let's check out some examples. The first one, find all critical values of f of x equals x cubed minus 9x squared plus 24x minus 10. So step 1 is find critical values. How do we find critical values? Critical values are the ones where either derivative is 0 or critical points or derivative is undefined. So let's find all the points where either derivative is 0 or derivative is undefined. F prime of x in this case is 3x squared minus 18x plus 24. So let's 3x squared minus 18x plus 24 is equal to 0. Because the derivative is a smooth continuous polynomial, derivative is never undefined. Because your derivative is a polynomial in itself, so this is never undefined. We don't have to worry about f prime of x being undefined, but this can equal 0. To make my life easy, I'm gonna divide everything with a 3. My new equation is x squared minus 6x plus 8 equal to 0, x minus 4, x minus 2 equal to 0, x equals 2 and 4. So these are my critical points, 2 and 4. That means if this graph has any max and mins, they can only occur at 2, x equals 2 or x equals 4. If this graph has any max or mins, they can only occur at x equals 2 or x equals 4. And the max and mins are actually the y values. So the absolute max, the local max, absolute min, local min are the y values, but they occur at these x values, which we call critical points. Check out another example. Find the absolute max and min of, in the last example, we were only looking for critical points, so we can stop once we find the critical points. This example, we need to find the absolute max and min of this function on this interval. Our extreme value theorem tells us if we're looking at a closed interval, we do have an absolute max and an absolute min in that closed interval. So they do exist. There's guarantee that we have a max and min, absolute max and min. So let's go ahead and find the derivative. Derivative is 3x squared minus 3, and find the critical points. Critical points are the ones where either f prime of x is 0 or f prime of x is undefined. Now, in this case, f prime of x is never undefined because never undefined. It's never undefined because derivative is a polynomial function. So this is never going to be undefined, but the y prime can equal to 0. 3x minus 3 can equal to 0 if x squared minus 1 is 0, which is x plus 1, x minus 1 equal to 0. So my two critical points come out to be -1 and +1. Now we're only looking at the interval 0 to 2. So I'm going to forget about the -1 because that does not even lie in my interval. And why am I including the endpoints? Because the absolute max and min can occur at the endpoints. When x is 0, what is y value? The absolute max or min or global max and min, any extreme values, they are going to be your y values. So find out what is the value of y when x is 0. When x is 0, y also comes out to be 0. When x is 1, y comes out to be 1 minus 3, which is -2. When x is 2, 8 minus 6 is 2. Now looking at this graph or table, we can tell we were looking for absolute max and min. So in this case, absolute max is y equals 2. It occurs at x equals 2. And absolute min is y equals -2. It occurs at x equals 1. Okay. Find the absolute extrema of f of x equals x squared minus 4 over x squared plus 4 on the interval -4 to 4. Okay, so first of all, I need to find the f prime of x, and then critical points are the points where either f prime of x is 0 or f prime of x is undefined. So I have to use the quotient rule here, x squared plus 4 squared, x squared plus 4 times derivative of numerator, which is 2x, minus x squared minus 4 times derivative of denominator, which is 2x. F prime of x turns out to be 2x to the third plus 8x minus 2x to the third minus 8x over x squared plus 4 to the second power. Let's clean up. In the numerator, looks like I can get rid of. That leaves me with 8x. When we subtract, it's actually going to become positive. 16x over x squared plus 4. Because of the negative in the middle, when we distribute the negative sign, it's going to become positive. 16x over x squared plus 4 squared. Now, is this derivative ever... This derivative is equal to 0 when 16x over x squared plus 4 squared is equal to 0. And that's going to happen when x is equal to 0. Is this derivative ever undefined? Now, is there any value of x that's going to make 0 in the denominator? No, this is never undefined. So x equals 0 is my critical point in this case. That means if this function has any max or mins, it can only occur at x equals 0. And because we're looking at a closed interval guarantees the absolute max or min, and that can happen at the endpoints as well. So let's go ahead and make a table of the values. With the given x values, we are going to check -4, x equals 0, and x equals +4. So when x is 0, the y value turns out to be 0 minus 4 over 4 is -1. When x is 0, y value turns out to be -1. When x is +4, 4 squared, 16 minus 4 over 16 plus 4, that's going to be 3/5. And when x is -4, same thing, that's going to be 3/5. So in this case, this is my absolute min, and these are my absolute max. There's more than one point where I have the absolute max. The absolute max is 3/5, and it occurs at x equals -4. See another example. Find all the critical points and the extrema. So we're looking for the critical points as well as the extrema. Now, extrema can occur at the endpoints. The local max and min cannot occur at the endpoints, but absolute max and min can occur at the endpoints of a closed interval, because your endpoints can be your max or min. So let's go ahead and find the derivative. 4x minus 8, and set that equal to 0. 4x minus 8 is equal to set. This is never undefined, but this can equal 0. 4x minus 8 is equal to 0 gives me x equals 2. X equals 2 is not in the interval. So not in the interval. That means x equals 2 may have a max or min for the function, but it's not in the interval I'm looking for. So I'm not going to bother to check it. I'm just going to check the value of y when x is -1 and the value of y when x is +1. When x is +1, 2 minus 8 plus 9. That's going to be a 3. When x is -1, that would be 2 plus 8 plus 9. That's going to be 19. So this is your max, absolute max, and this is your absolute min. Find all the critical numbers and extrema of x plus 1. F of x equals 1 over x plus natural log of x. We're looking between 1/4 to 4. Okay, let's go ahead and find the derivative f prime of x, which is x to the power -1, negative x to the power -2 plus 1 over x, which gives me -1 over x squared plus 1 over x. Cleaning up, x squared, -1 plus x, or x minus 1 in the numerator. X minus 1 in the numerator. So this is my derivative. So this derivative, f prime of x, is equal to 0 when x minus 1 over x squared is 0, which gives me x minus 1 is 0, which gives me x is equal to 1. And f prime of x is undefined. This derivative is going to be undefined when x minus 1 over x squared is 0. This is actually going to happen when your denominator becomes 0, so when x is equal to 0. Now this is not in the interval, although you may have a max or min in at x equals 0, but not in the interval that we are looking for. So not in the interval, I'm going to ignore the x equals 0 and go ahead and make a table. Remember to include the endpoints, because you can have an absolute max or absolute min at the endpoints at 0.25 and 1 and 4. When x is 1, y turns out to be 1 plus natural log of 1 is 0. Y is 1 again. When x is 4, y turns out to be, let's use a calculator. Y turns out to be 1.636. When x is 0.25, let's see what does y turn out to be. Again, we are plugging in here to find the y values. Okay, we are plugging in to the original function to find the y values, not in the derivative function. Okay, that turns out to be 2.614. 2.614. So here we can take a look, your min and max. So this is going to be your absolute max, and this is going to be your absolute min. Now you might say, what is happening in this interval given 0.25? Oh no. Yeah, that's correct. This is going to be your absolute min, and absolute max is 2.614. That's absolutely correct. Okay, another function. Find the critical numbers for this. F of x is equal to x to the power 2/3 on the interval -2/3. Okay, so first we want to find the critical point. Critical points are the ones where derivative is 0. Let's go ahead and find the derivative. X to the power 2/3 minus 1 is going to give me -1/3. So f prime of x is 0 when 2/3 x to the power 1/3 is equal to 0. This function is never going to equal to 0. And this function is going to be undefined when x is equal to, this function is going to be undefined when x is equal to 0, because we have x in the denominator. So my critical point turns out to be 0, and it's in the interval. So I'm going to go ahead and make a table, -2, 0, and 3. When x is 0, the y turns out to be 0 as well. Again, you plug in here to find the y values. Okay, when x is 3 to the power 2/3, use a calculator. That's going to be square root or cube root of 9. Cube root of 9. If I plug -2, that's going to be cube root of 4. So looks like I do have an absolute min here, and I do have an absolute max here. Absolute min and absolute max are there. Okay. Now, if you want to find out if -2 is a local max or min, go ahead and pick the values. First of all, we're not really looking at to the left of -2, so ignore that. But if you were looking at entire interval, then I would say go ahead and pick the values. Oh no, no need to do that. -2 was not a critical number. Ignore. Yeah, we wouldn't do anything more. This would be absolute max and absolute min. Okay, another example. Find all the critical numbers and extrema of this given function. So critical points are the ones where either derivative is 0 or derivative does not exist. F prime of x is 0. F prime of x does not exist. Okay, so f prime of x is 1 over 2 square root of 1 plus x squared times 2x minus 2. Cleaning up, we can cancel this 2 and 2 here, x over square root of 1 plus x squared minus 2. In order for me to find where derivative is 0 or where derivative does not exist, I need it in the nicer shape and form. So I think this is okay. So f prime of x is equal to 0 when x minus 2 over 1 plus x squared is equal to 0. That means when x minus 2 is 0 or x is equal to 2. And f prime of x is undefined. And that's actually never going to happen because there's no value of x that's going to give me 0 in the denominator. So this is never. So that means I'm ready to find out my absolute max and min, my extrema here. Let's see. Your absolute max and min can also be your local max and min. For example, in case of y is equal to x squared, this point is absolute min. It's also local min. Okay, f prime of x is undefined. This is never, so make a table. X equals 2. It's not even in the interval. Not in the interval. That means I don't need to worry about the point x equals 2. It may have a max or min at x equals 2, but we're not looking at it. We're only looking in between the interval 0 to 1 and see if there is any max or min for the function. When x is 0, y would be 1 minus 2, which is negative 1. When x is 1, y would be square root of 2 minus 2. So there's going to be my max, and there's going to be my min, because that's going to be smaller. Actually, when I plug a 0 in there, square root of 1 minus 0, that would be just a positive 1. Positive 1. Okay, find all the absolute extrema, or f of theta is equal to cos theta plus sine theta. Okay, so this is my function. And we're looking for any absolute max or min, any highest possible point or lowest possible point from the interval looking at 0 to 2 pi. Okay, first find the derivative. F prime of theta would be negative sine theta plus cosine theta. Now, we know these are smooth continuous curves, and this is sum of two smooth continuous functions, and these are going to be never undefined. Neither sine x nor cos x, they're never undefined going from the 0 to 2 pi. So f prime of theta is never undefined, but f prime of theta can equal 0 when negative sine theta is equal to cosine theta. Or we can say no, that's not going to be correct. Negative sine theta plus cosine theta is equal to 0. We can say when cos theta is equal to sine theta, that's when the derivative is going to equal 0. When is the cosine theta equal to sine theta? That happens at pi over 4, and it also happens at 5 pi over 4, because in the third quadrant they both are negative. So theta is equal to pi over 4, 5 pi over 4, both are in the interval. I'm ready to check my maxes and mins starting from 0, pi over 4, 5 pi over 4, and 2 pi. When x is 0, the y turns out to be cosine of 0 plus sine of 0. It is 1. When x is 2 pi, again, I have a 1 here. Pi over 4 cosine pi over 4 plus sine pi over 4, root 2 over 2 plus root 2 over 2. That would be root 2. And it's going to be negative root 2 in this case. And there's my max, and there's my min. That's all about extreme values of a function. So if we're looking at a closed interval, we will definitely have the extreme values. We will definitely have the lowest possible point or the highest possible point. They can be your endpoints. And when can we have a max or min? They can only happen at the critical points. Critical points are the points where derivative is 0 or derivative is not defined. Now, not every critical point will give us a max or min. Not every critical point will be a max or min. It is possible that the critical points can be your max or mins, but not every critical point is a max or min. So you have to check. Now, to find the local max or min or relative max or min, we will have to find the critical points and then look for around the critical points. If that critical point is lower than the neighbors or higher than the neighbors, then that can be your local max or min. That was all in this section.